went through 5 on your desk so I could kind of finish looking through, make sure to see how far we got. What if this is not common sense?
None of it. Well,
Effusion is a new term, right? So the first one, you're like, yeah, gases have low density. What do they do in here? They're floating, right? Gases are floating. They're everywhere, so they have low density. And gases, whenever we discuss like the units of density, you always tell me density is grams per milliliter usually. Well, in gases take up so much space. So instead of recording it per milliliter, we actually record it per liter. And that's just one small difference. And you might see that, but you may not. Compression, you guys box of air? Is there room between the gas molecules to compress them?
Yes.
Yes, compress them. Is there, if you wanted to make more space between the gas molecules, what would you do to them? Allow the container to expand. So that's just what I mean here by decreasing space between the atoms or increasing space between the atoms. That's compression and expansion. You can put your box away now. Diffusion. If I brought in a box of Krispy Kreme donuts, because they're half price, they're trademark scent particles flying around, right? What would happen when I brought them in here, chemistry-wise?
Eat them.
Chemistry. Scent particles.
They would like travel to.
What's the word for that? Diffuse across the room, right? So you'd smell them first, and then who? The waves, and then and so forth, right? So they're moving because they have kinetic energy. They're moving. That's the energy of motion. So what if let's just scenario here. My favorite, just so you all know, my favorite is the chocolate-covered cream filling. Oh, so good. Let's say their particles, like chocolate-covered cream-filled donuts, have a special scent, and let's say they are 48 grams per mole. And let's say the generic, like just glazed ones, let's say they have a lower mass. Let's say they have 30 grams per mole as their scent particle mass, right? Which of those particles would move faster? Which one? The lighter one. So the normal one, the normal glazed ones, those scent particles would come to you faster, and then the other ones would stay right here with me. They would move really slow because I'd probably eat them before they even actually made it out of the room. But so basically, you already know that. Light things move fast, heavy things move really slow, and so that's what this equation is referring to. Kinetic energy is the average kinetic energy is related to the temperature which the gas particles exist at, okay? But if I tell you that this average kinetic energy is constant, if I increase the mass here, what has to happen to velocity? They would slow down, right? Heavy things are heavy, high mass, they have a slow velocity, and vice versa. Light things, low mass, they have a high velocity. I always use the example of my little brother. I mean, he's like this tall, but he's still younger than me. He was a wide receiver of some sort, and I went to like every game. That's all I remember. And he was going downfield, little skinny guy, flying down the field, and he goes to catch his touchdown pass. He's there, catches it, guy flies into the side of him, and he lands on his elbow, and out comes his arm, like the bones that just came out. But he still made the touchdown, so he's very happy with himself. Yeah, that's all that matters. He had bones and cartilage and tendons and stuff. Emergency surgery. My mom's the athletic trainer. She's like, my baby! And I'm just like the water girl going like, what happened? Oh, it's my brother. Oh man, I hope he's okay. So anyway, fast things are lighter generally. Slow things are usually heavier. Okay, so that's the diffusion debate here. Effusion is something that we've all probably experienced. We've all had birthday balloons, yes? Yeah. What happens over time? They deflate, right? They're gone. But why?
Because they're stationary.
Because what's on the latex? Yeah. Tiny pores or holes, right? And those little tiny holes allow gases to escape. So, would you rather have a balloon that's filled with carbon dioxide or a balloon that's filled with helium? You want helium for the moment, because that's like, oh my gosh, it's floating, yay, and you can suck it in and your voice goes higher, right? We've all experienced that. But what's just going to last longer? Why the carbon dioxide?
Because it's bigger atoms, so they can't fit through the pores.
And they're moving slower, so they're just naturally escaping at a slower pace. So the balloon that's filled with carbon dioxide might last you 2 weeks, or the helium one might last 3 days. Okay? And we all want balloons for a longer time. Even if we don't sit on the ground, just tape it to the wall and pretend it's floating, okay? So that's how you do it. I'll show you guys a video. I'm going to show you a video. I'll show you a video. Hold on. Sulfur dioxide. Oh. Hexafluoride. Sorry, hexafluoride. All right, so we're just gonna pretend this works. Okay.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
Well, simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that, and my voice gets really low, although somehow I'm still funny. It's scientific!
But how do you get that out?
You have to go really deep.
Well, you could exhale, but well, my computer's being like real weird. No, you actually, it's really, really dense. So yeah, you can compress your lungs and like force it out, but what would be easier to get it out? Do a handstand. Come right out. More dense, and so your mouth needs to be like on the ground. What? It falls right out. When you're upside down, it spins out. And your ears are still.
I feel like you're being sarcastic.
No, I'm serious. Like that's what you do a handstand and you let it out. Okay. Let's talk about. Well, not this one. Let's talk about. I'm gonna go ahead and do Dalton's law while I'm thinking about it. Right here. Dalton's law is number 9 on your PS. Okay. PS 14. We've all started. Great. How far have we gotten? Number 6. Number 4. Through the true false, please, Lord. Okay. Let's make sure we know that. This is Dalton's law. This is on your foldable. You've probably seen it before. Let's just do a quick example, and then that's done for Dalton's law. The one we're going to talk about tomorrow is the last one on your foldable that we've not talked about, which is what? Graham's law. We'll talk about Graham's law more tomorrow. Okay, so Dalton's law is literally the easiest one. It's adding. I think you learned that like 2 days ago. Remember how to add? Remember, right? Okay. Didn't want to have to teach you how to add. It is total pressure is equal to, so pressure total is like every gas present that causes pressure, yeah. Okay, and what did you guys write in your foldable? What did you write in your foldable for this? Right, and I just go PA plus PB plus PC, da-da-da. It just depends on how many gases are present that's causing this total pressure. So for our atmosphere, what are all the gases you can think of that are in our atmosphere? Uh-huh. I heard oxygen. Argon, what else? Yeah, I'll say ozone, O3. What else? Carbon dioxide. And that good stuff we all need. Water vapor, thank you. Water vapor. We all need water probably, I mean, not more than oxygen, I don't know which we need more. Both. Okay. So if these are all of them that are present, yeah, then these together collectively make P atmosphere. So then this would be like P atmosphere. This is a good example if you don't have an example in your foldable. P atmosphere is equal to P of nitrogen gas plus P of oxygen gas plus P of argon gas. Da, 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 da. You get the point. You add them all together. And so an experiment we're going to do tomorrow is going to incorporate us taking some gas, putting it underwater, making a bubble through the water. What do you think comes with the gas though? If I'm bubbling it through water. If you took a straw and you made bubbles into like a soda or into like some water, the bubbles are going to start coming out, right? But there's little water droplets that come out with it. That's actually water vapor. It's a gas, but it's just called water vapor in this case. So in our case, and on one of the questions, you'll have on number 9, it says the partial pressure of hydrogen sulfide is what it's asking for, and it tells you something about it's collected underwater by water displacement. This is a value I did not give you on number 9, so you got to write it down. I'm actually going to just go ahead and do number 9 right now. On number 9, on that one, on 14. And I neglected to give you the partial pressure of water vapor, but here it is now. Partial pressure of water vapor at 27 degrees C is 3.73 kPa. Okay, and that value is just standard value. It's found in the textbook. It's not something I ask you to know. And it's specific as, like, this is specific pressure, bless you, at 27 degrees C, because temperature is water vapor pressure is dependent upon the temperature. So it's like, when I tell you the temperature, it really doesn't matter. It's just something to tell you. Just like when you finish a sentence, what do you put at the end? Period. It's just a given. Like, it's always going to give you temperature. Do not worry about it. Number 9, it told you the total pressure was 207.3. 33 kPa. So if I know the total pressure, and I know the vapor pressure of water, and I don't know this, what do? Subtract. That's it. This is the easiest gas law. Okay? You just take the big number, total pressure, minus the partial pressure of water vapor, and that gives you the partial pressure of the gas. That's just embedded in the column. And the way that this lab is done is through water displacement. It's where you put a beaker or a bowl down, and then you take this graduated cylinder, and you flip it upside down. Like that. Remember our pictures we drew? We're going to do that tomorrow with water and gas. Okay, so that's Dalton's law for you. How about them 1 through 5s? Let's look at that right now. Which of these do I need to do? I'm only going to do 1 or 2 right now. Yeah. Which one? 3. Starting with number 3. Please pull this out. I'm expecting that you have your givens written down. I'm expecting you at least have your BCE givens and at least the start of the ideal gas. Because we kind of walked through 1 or 2 examples, and I'm challenging you to figure out what's going on here, okay? So this is the synthesis of ammonia. Synthesis of ammonia means producing ammonia from its elements. So we all got our BCE. 3 and 2. Did we get that far last week? Or Monday? Whatever. Okay. So the question is how many grams of nitrogen are needed to produce blah, blah, blah. What those conditions that are given, what is it referring to? What is it about? Which reactant or product? Is it about what? So it says it produces that many liters of ammonia at that temperature, at that pressure. So what are all these conditions referring to? Ammonia or nitrogen or hydrogen? It's actually more about ammonia, okay? Because it says I'm collecting that many liters of ammonia at these 2 temperatures. Now these 2 things could be a present, it will apply to all of the other molecules, but specifically I want to make sure you're focusing on ammonia. And then the question does not ask for ammonia. The question asks for nitrogen, right? So when we go through this math, whatever we get in the end is regarding ammonia. So how do you get back to nitrogen? Mole ratios, right? So you just really have to label things, just so you're not confused. So if I have T, P, V, what am I looking for? I have the blank. So I have V, T, and P. I'm looking for N of ammonia. And then I'm going to take N, or moles, and convert to other moles, and then go back to find grams. So, sorry, I didn't mean to just write on that. But my question is to get to grams. I have volume of ammonia, temperature, pressure, and I went ahead and converted to 0.7 atmospheres. So I must find the N of ammonia, and then do stoichiometry to find more information about nitrogen gas. So what did you guys get for, you probably already did PV equals NRT. Who got N here already? Raise your hand. Who got N? I want to know who got N. 3 people in our class. 4 people in our class. There wasn't much else you could do here, right? You didn't find like ponies and puppy dogs. There's nothing else you could find but N. So N of ammonia, the rearrangement of the variable is PV over RT. And then what did you get when you plugged in your variables? Yeah.
Is it 1.468?
1.468? I think that's right.
1.463.
3, 1.4. I'm just going to stop it at 6, yeah. I mean at 4.6, yeah. Okay, so that's how many moles of ammonia you produce. Then how do you get to nitrogen? Okay, go for it, Bryson. Tell me what to do. Okay, so 1 mole of nitrogen because of the BCE. 2 moles of ammonia because of the BCE. And then? And 1 mole of, sorry, I don't know where I put ammonia. Nitrogen. So 28 came from what though?
2 nitrogens, and nitrogen weighs 14 plus 14, so we get 28. And then, what'd you guys get? 20. I have 20.44 for some reason. But if it's 20.5, then we're still close. It's all good. Oh, it's because I used 28.012 or 02. This is grams of nitrogen. Okay. And so I'm asking for you to plug your values in. I just did this very quickly to show you how to do it. All right, let me do one more right now. 5. So 5 gives you a scenario where you create sodium chloride, because it says like the synthesis of sodium chloride. It tells you sodium metals reacting with chlorine gas, but it doesn't tell you anything about really about the chlorine gas. It tells you the temperature and the pressure at which it's collected. It doesn't tell you the volume. It doesn't tell you amounts of it. So this is not an LR problem. Okay. This one you're going to start off with your sodium metal to find what you need to whenever you need to do it. But first, the question says, what volume of chlorine gas is needed to react? So our question is what? V, right? So we're looking for V. We're given P and T. So what else are we missing? N of chlorine gas, right? So you're assuming that if you have this much sodium metal, whatever sodium metal you have, you should have enough chlorine gas to react with that to make sodium chloride. So how would I figure out N of chlorine? And then get from moles of sodium to moles of chlorine, how? The mole ratio. So we can find N, and then we'll later plug it into PV's on RT to find V. Okay, so here.
So really the only thing you need the VC for is when you convert.
Yep.
But so it's kind of like irrelevant until you get to the last one.
Yep. Sometimes we do stoichiometry on the front side of the problem, sometimes we do on the back side. So okay. I'm kind of doing it, yeah, right now I'm actually going to do it first, and then I'm going to plug in the PV's on RT, and then we'll do it again. So it can be it can be a before or after, or both. But it depends on what you need. So in this case, I'm looking for volume. I have T, I have P. I have the mass of sodium, but then I need to figure out how to get to V because I'm missing too many variables. So that's why I have to use sodium to get to moles of chlorine before I can move on. So here we go. The sodium 4.6 grams of sodium is 20, let me rewrite this. 4.6 grams of sodium is 23 grams of sodium per 1 mole of sodium. And then from here, what? Say again? So sodium is going to have a 2 with it, 2 moles of sodium, 1 mole of chlorine gas, and that's going to be N of chlorine, which is 0.10 moles of chlorine. This is N. And I just label my N's a lot of the times to indicate what it's talking about. Okay, so then from here, Ian, how do you get to volume of chlorine gas? So we just took PVs and RT, you rearranged it, plug in each of your variables to their specific units, or at their specific units, and what do you get for V?
I got
2.6 liters. It should be, I think it's 2.6 if you guys did it without rounding. 2.6 liters-ish of chlorine gas, whenever you plug everything in appropriately. Okay, so that's chlorine gas for you. On the key, I did not fix it. I think it said 5.2 is double. That's probably why more than anything you guys were like questioning this particular one. The next question said, from those things that are reacting, how much sodium chloride can you make? Well, if you know actually exactly how much sodium metal you have and how much chlorine gas you have, you've made them equivalent to each other, like exactly that amount of sodium chloride will react with exactly that amount of chlorine gas. There's no limiting reagent. They actually both exhaust each other at exactly the same time. So it doesn't matter if you start with that or if you start with that. You can go through stoichiometry to get to sodium chloride. So I'm just going to start with this sodium metal because I've already kind of got the setup here. But here's sodium metal. 1 mole of sodium metal is 23 grams of sodium metal. And that relates to sodium chloride in what ratio? 2 to 1. Because it's 2 sodium chlorides to 2 to 2 actually, right? 2 sodium chlorides to 2 sodiums. I'm using sodium. If you use chlorine, then yours will be slightly different. So that's, what is it, 2 to 2? 2 moles of sodium chloride to 2 moles of sodium. And then grams, what's the molar mass of sodium chloride? 58.55. So it's like 0.2, like, what is that, 7 something? How many grams is that, guys? How many grams is that? Grams? We're like, we have to use our calculator? What? Thank you. My calculator's not working. Okay. There you go. So, I'm going to hold off on going over more of these right now because there's one on there that I definitely want to go over, which is the LR one for number 2. Yeah, I think number 2 or number 4. One of them I want to definitely go over. So, right now, go ahead and go to my website. If you're not already there, go to my website. And I want to tell you what we're going to do for about 30 minutes here, so you can visualize more of the kinetic molecular theory and kind of what's actually happening behind the scenes here. Go to Honors Chem Unit Docs and go down to Unit 5 and you'll see gas law simulation. Okay. And the link here will bring you directly to the simulation, but the document is below it. So when we get to this, you guys might want to partner up so you can have one person with simulation up and one person with the document up because your laptops are kind of small. But when you click on the simulation, it looks like this. Let me reset this. So it indicates to you kind of what to do. So it'll say, okay, put 1 pump of gas in there. And the pumper is here. Oh, let me just restart it. Let me show you from the start. So you can download it and it's Java. It'll ask you for some permissions. Under Documents, Unit 5, go ahead and download the viewer. Some of you might be ahead of me here. Mine's slowly starting up. There we go. So it's like, pump the handle, pump the handle. That's what it's telling you to do, right? So what are you gonna do? Pump the handle. And you can reset it if you do, but you can see like the gas particles come out, and then you're gonna be using this little man to like compress the gas and expand the gas and so forth. You'll be using the heat controls to change some things, but there are specific directions under the document that if you download the doc, it looks like this. So the very first thing you see are just boxes where you're gonna be indicating like 10 molecules of gas and drawing them with how fast they're moving based on the specifications. But this does not require the simulation at all. Take less than 5 minutes to do that. Okay? You guys looking up here, I know you got like, you're looking down the laptops, so make sure you're looking up here too. Okay? This does not take very long. Take less than 5 minutes. Then it tells you to click the simulation. It tells you exactly what to do, okay? So, take 30 minutes. Questions? Let's do this. Spread out if you need to have some space. But I'm expecting you're on task to get this mostly done. Leave your 1 through 5 on your desk so I can see how far you got. Yep, write it on paper. If you work with somebody, both of you are writing, because both of you will have different, like, later on you'll finish it, and you're going to need the paper. But you can look on somebody else's computers, that's what I was educating.
out like what the little particles look like.
Yeah. Where are those questions?
They are back in the web page underneath where it says right under the link.
Okay, did you get that already done?
Yes.
I put the reagents away on that.
I'll come back and help you. I need to check some homework though. I'll come back in first.
Partners there. Both next week.
Separately, because you guys are you're both going to need it for reference.
And then long arrows you can go off. Short arrows you can Struggling? Yeah, you think so? It is like pointing from the little particle. That's fine. What are the arrows for? Like, I think it's like the long ones you draw. Like, do you want to put them in the box or outside? I just put it like that. Like, this is what happened. It's like the longer the stick part of the arrow is, the more velocity they have. So if it's like because they're moving and so that's where they are moving. That's where they're living their life. Like if it's high pressure, like high pressure don't move more. More things. Yeah. So yeah. If it's a high pressure, like I think it's more like it's They would move closer with each other.
All right, guys, listen to me attention for like about 30 seconds. Eyes up here. Whenever you're drawing, it's actually you're like, I'm just drawing. No, there's a lot of thought behind it. Okay. First of all, how many particles are you drawing? 10. And then what do you draw to indicate they're moving fast? A little tail, right? So if you're just drawing dots, it's wrong. That's easy. Okay. You can read. I know you can. And then when it's low temperature versus high temperature, what's really going to be the difference? You're going to have 10 molecules here, 10 molecules here. But what's going to be the difference? Okay, so who's moving faster? The high temperature, okay? What exactly is the reason that causes pressure?
Pressure's like when they hit against the edges of the container.
Okay, so if they hit with the sides of the container, they're causing more pressure. So when you're drawing a high pressure system, you're going to be drawing them moving faster because they're hitting the walls more frequently. Okay? That's it. Okay? Right now, if you just have your computers out, you don't have your cell phone out, you don't have your earphones out, you don't have anything else out except for the computer and you're working. Okay? You should already be almost done with that part. If you've not progressed that far, get there. No, it's not them closer together. It's not collisions with each other. It's collisions with the container wall. So they're hitting the wall more often.
I just did that when I have my class.
Once you found those important it's
I had like a bus pass for the struggle lessons and I'm like, you don't understand. There's unbound. I've got weight for the one I get home today. Did you just call her awful? Oh, I thought she said that. I was like, no.
Then how about I'll do another one.
And so the volume ones are like big box, little box.
It's the metal copper. Or zinc. Either copper or zinc, but they're right next to each other, so. Oh, but they live 4 2 much charge, so I feel like
For the high volume, low volume, that's the size of the container. Oh, that's not done all the way. Yeah. How did you put that? I just like
your brain remembers.
I highlighted my definitions and I put that in with like all my other stuff. It's like style, yeah.
I'll come to you.
This is 15. Can you put the white? Yes. Yeah, like lights. I think, yeah.
Hey, do you know like what's the first particles? What happens to the compound particles? They disperse. What happens to the compound particles when they come in one time? I was looking at them and I was like, maybe I need some more to look at, and then it went down. They don't always move in the same direction. Because they're bouncing everywhere. Yeah, and then they like hit against each other. There's something I don't know. I have to do the fall festival. Wait, it's this week. Yeah. I have to do fall festival from 7 to 2 and then at work from 4 to 11. Girl, how are you doing that? That's not right. It's like not helping. I'm like, wait, that's this week? Yeah. Okay. I signed up. Yeah. I like was looking at my little planner and I was like, I get 2 hours in my phone to just cry in the shower and then get ready for work. I made it the work. I know. Like, you were talking about quitting last night. Like, literally, yeah, what are your feelings on putting in my 2 weeks? I was like, same girl, same. We just do it together, same paper. You take the front half, I'll take the back half. Since you're hiring new people anyway, we'll be good. And then, like, one of our managers were there, and it was just like, she's just like, really glad that each other. Like, yeah, like, I'm still in training, right? Like, I can't get a job anywhere else, but I'm gonna get my job here. Chick-fil-A. I doubt anybody else. And yes, there's some places that pay so much more. They don't teach you. You know people at Aldi, they sit in chairs and throw cans, they get paid $11 an hour. You know what at Aldi? Subway gets paid. Okay, Subway gets paid like $7. Yeah, thanks. But they don't ever do anything. They just in the back.
So we're done with this part. Is that what's in? Yeah.
No, there's actually not really more. I went over the other day, and there was a guy there who seemed pretty chill.
Why did you put the C on number 2 in part 1?
Not in number 2. I've just finished all of number 1, and now I'm on YouTube. We'll find something. But yeah, she doesn't like them. Which is not.
I'm sorry, I for a different thing.
I have a whole plan of graduating for me. I'm not trying to be here right now.
There you go.
It definitely depends on how small the parcel is, the higher the attachment.
Is it just because you added more? Like, it's just because you added more.
Yeah, I think so. So the larger the particle, the more the pressure.
You never figure out that, and then do like whatever your species that are heavy. I love that. First part.
It's like this.
Make it of that. It's probably honest.
No, I don't know something. I look like
Probably not.
huh?
I copied the roll. Just go over here with I'll calculate both. It's probably your both of those. So what were your two pressures?
They were both oh, I could have gone.
Oh, look at that.
Does it last long?
Oh, it's gone.
It's not about the mass of it, it's about the collision. Does it collide? And we'll talk about that. We'll wrap up on that. Okay, so about 10 more minutes. You should go get through part 3 or 4 at least.
Was your outlet pressure about the same?
This is a one inverse. So you decrease the volume.
I think it's inverse. Okay, wait.
Have like both legs in a cast with a wheelchair. Yeah. Just watch what they do.
I've got a lot of help on that, so I'm not working on it.
There's those. Let's not ask you. We're expecting this is what happens. When you start, like right now, I'm at almost 2,000 views. Yeah.
right on the purple. Yeah, no, we didn't. Yeah. I was like, how are you actually finished for?
You ready? Look where there's 100 atoms. Right
You just type in the number and all you can see it. No, because I'm just pressing like down up there.
I thought you were gonna go.
I still took home Spanish today. She's in the house. First row of the bag. I was like, you just didn't even know that? No,
Yeah, there's very easy. Not on the exam. Yeah, I mean,
Alright guys, take one more minute. I'm trying to teach another class too. So take one more minute, work on problem set 14 until I come back. Okay, do not play. Problem set 14, yeah. If you're done with computers, come up, yeah. Wait, no. I'll be back.
What the heck? I answered all the questions in 5 minutes. Because this is what happens to the pressure. And I said, volume decreases, pressure increases in an indirect relationship. And then the next question is, as volume goes up, pressure goes down. Or no, it's like indirect. Yeah, I took some
Wait, did you tell us his homework?
Oh, yeah.
I didn't hear you say it. Let's hope she didn't say that. She just says finish this. Yeah, usually she's like, oh, these maps are just right at the end. Oh my gosh, no, it's 15 minutes left. First 6, yeah. I got 135 species and then around 7.3 to get it. 135 species, 7.3. I'm just missing the 7.9. Oh, yeah. Struggle with seasons right now. I no longer care about that struggle, as you can see. And it's nice to just be so you know, like I might as well do like these are supposed to be like cuddly. What did you say? I said athletic. No, this is the if I could just wear them. When they bump into each other, when they collide. For number 7, which is for this one is because there's no
Alright, lovely people, put laptops up in 1 minute, please. Thank you. Take 1 minute and laptops go up.
What part should we have gotten?
4. Hope. Hold it for now. It's in your portfolio check. All right. You have 30 seconds to get those laptops up. Log on.
I tried, and this is on different color pen. You just can't.
Yeah, okay. I got you. It's good because you use colorful paper. I think I had to check one more person's homework. All right, and if you don't have your laptop loaded up yet, hold it. You'll put it up at the end of class. I have 2 questions I'm going to be doing in approximately a minute. So hold your laptops for now. You're getting the class. No worries. We got 15 minutes left.
I got a haircut to get to it.
I'm going to be going over some work.
Okay,
Okay, I see. I'm almost to that row. You're my last row. Alright guys, give me your attention. We gotta get 10 seconds. Sit down, let's go. Sit down, sit down, sit down. And eyes up here. Phones away. 1 through 5 out. We're gonna go over number 2. Have your simulation out too. There are 2 questions on here I need to talk about to clarify what was happening during simulation. Sorry, I was trying to help the other class because they are in need. Please put your phones away. Thank you. So the kinetic molecular theory, we talked about all the characteristics of gases that we assume. Now we have to actually see some of them. One in particular that I want to approach is the one with pressure, with the heavy species versus the light species. What was the difference in your heavy species and light species, Max? Your pressure. You wrote it down on 3.
Yeah. Well, when you put 100 heavy species, the pressure would be higher than the light species because of how much the mass.
Is that what I want to see data though? You're making assumptions. Who's got data?
Both of my pressures were the same for mine.
Okay, and that's what you should have seen. It's probably not what you thought you would have seen, but that's what you did see, right? So why? Heavy particles are moving fast or slow? Slow, so they hit the container wall, right? With a lot of force because they're heavy, but not a lot of force because of their lack of speed. Small molecules are moving fast, but they're not hitting with as much weight behind them, right? So they're hitting fast, but there's not a lot of force behind it. So actually they both negate each other, basically. So the heavier they are, the slower they move. That makes them collide with the same amount of force as moving fast and weighing less. So it makes them collide at the same frequency, and that's why the pressure is pretty much spot on. There's an insignificant difference. So that was one thing you should have seen. And then down on the temperature, this one, Charles' Law, Part 4. Tell me what you guys would have seen here. As the volume, as the temperature, let's say the temperature increases. Temperature increases, what should happen to volume for Charles' Law? Why? It is a direct relationship. They increase because what if okay, so they move more, they should be colliding with the container wall more often, right? But what would that do to pressure? Increase pressure, and we're like, nope, can't increase the pressure. The pressure was not the pressure is a constant here. So to counter that, to alleviate the pressure, you have to increase the volume instead to make them collide with the container walls less often. Okay, hold your simulation. If you did not finish through part, I'll let you know. I'm hoping you guys got through part 4-ish, and if you need more time, you can come back during teal or come back finish on review day. But this is something I'm going to take up in your portfolio check, so that's why I said write on separate pieces of paper and hold on to it. Okay. Let's look at number 2 on the ideal gas law practice. Check over it with me, even if you know you got it right. Okay. I just want to make sure you understand what you're doing so that you can finish the rest on your own. Okay, so you're given magnesium and hydrochloric acid. So we already know the reaction. Magnesium hydrochloric acid. This one, and I already have the answers up here, my bad. You're given givens.
Okay, but you're also given information about the mass of magnesium and the volume and molarity of hydrochloric acid, so you don't know which one is going to be limiting the amount of products made. So that's why this is an LR column, but it's not specifying like I've got excess of this. I'm giving you 2 quantities. Do you see how you can know that's an LR problem off the bat? Some of us are like, yeah, this is LR. Okay, yeah. You should know off the bat it's LR. So what is the first step whenever you have these 2 quantities? To get to moles, right? So when you get to moles, you have your have, and my stuff got erased a little bit when I was cleaning this up from last class. So tell me, those of you who did this, how much did you have? So here's my have of magnesium, 1.5 grams of magnesium, molar mass 24.31 is its molar mass. So you got 0.047 moles of magnesium. That's how much you had of it. How did you get to moles of this one? Hydrochloric acid. Took the molarity, oops, 0.1, so 0.10 moles over liter times 0.150 liters, and that's the milliliters in liter form. So what is that for half of hydrochloric acid? Moles of hydrochloric acid. Okay. From here, that's what you have of both of them. How do you figure out how much you need of the other to fully react? Mole ratio, right? So the mole ratio between the two for magnesium to hydrochloric acid is what? Magnesium to, or hydrochloric acid on top. That's a 2, right? So 2 moles of hydrochloric acid over 1 mole of magnesium. Sorry, I'm writing very quickly here. So this gives me 0.0986. 4 moles of HCl. Okay, so knowing you need that much HCl, what can you automatically assume now? That's the LR because I need 0.09. I only have 0.01. So I'm going to run out very quickly, right, if you compare this to this. So that's going to yield us to be, this is going to yield to be the LR, this is going to be the excess. So the gas that we're making is hydrogen gas, right? So that's the gas that all these conditions are given about. The gas is collected at that temperature and that pressure, and then that gas, is that volume is that gas. That's the actual yield of the hydrogen gas that's collected. So we're deciding on percent yield, right? So what are we missing? Huh? We're missing the theoretical yield, but in like you said, in volume form, because it has to be the same units. It has to be milliliters of hydrogen gas. So we have T, P, and what else? No, see how this is saying, okay, this is saying that they collected this much gas, right? So that's actual yield. So I'm actually not going to use, I could, there's probably 2 ways to do this, but I'm actually going to see if I can not use that right now, because that's actual yield. I want to figure out how much theoretically oxygen I should be able to yield. So solve for N right now. Let's maybe calculate N right now. Let's calculate N through stoichiometry. And then we can plug in into the ideal gas law to figure out how much volume that should yield in La La Land theoretically. So how would I get to N of the gas? From who? Right, so the whole reason we did the LR is to use it, right? To use the half of the LR, which is 0.015 moles of hydrochloric acid, and then get to hydrogen gas. So that's a 2-to-1 ratio. So 1 mole of hydrogen gas on top, 2 moles of HCl on bottom. So that's 0.0075 moles of hydrogen gas. That is N of hydrogen. That is the N that we'll use in the PV of RT. So from there, what are we going to solve for? Volume, that's the theoretical volume from this LR. If it was perfect, it would yield this amount of hydrogen gas, and if that was perfectly contained, it would yield X amount of volume. So when you plug in, I'm not going to show you the conversion from milliliters mercury to atmospheres right there. When you do PV equals an RT,
they kind of just complex sometimes?
I usually will give you a bit more guidance, or if there might be one like this and the other ones are easier. Okay, so volume you saw for that by rearranging your variables, it was like, thank you, 0.187 liters. So that has to be converted to milliliters in order to compare the same unit. So this is 187 milliliters, which is theoretical yield. So, would you want this person in your lab? Why? What's their percent yield? 79. So you took 149 actual yield over 187 theoretical yield. 149 over 187. Oops, times 100. And what I hear, 79% yield?
79.3 is what I got.
0.3%. Good. I got something like that.
But I did 0.88.
It's close. We're good. So no, I mean, they're okay. They're not perfect. All right, we have 4 minutes left here. Let me give you a recap on what you're doing for semesters. Those of you who've already looked at the experimental design, thank you. You don't need all my feedback to start that. My feedback is really going to do a really good job of helping you prepare for the paper. But because the background information is all about the chemistry behind it, and that's really important, but that's not necessarily important to start your experimental design. So you should be deciding on variables you're testing, who's providing what materials to do the experiment with. Are you going to use my facilities, or are you going to be working at home? If you're using my facilities and my equipment, if you're using my equipment, you have to use it here most of it. Let's look at beaker. I'll send a beaker home back and bring it back to you. The chemicals wise, send it to my claim state here. How long are you going to be leading your test? What data are you going to be collecting? Are you going to be putting that data in a data table or a graph or a video? It can be qualitative data where you're looking through videos. Because at the very end of this, I will be approving your experiments or not, okay? So within, like, not on Friday, but after Friday. So I want to see progress soon. If I need to give you the weekend, I can, but that pushes back your time with experiment, right? Because if you need 3 weeks for your experiment, then we got to get this started soon, okay? So if you want to turn in by Friday so you can start sooner, that's totally fine. Laptops.
I tend to students around the bar, because 91 is from 7 to 4 today.
How much